Okay, so this is Cambridge exercise 2.5 question 3, and it's a regions question. And in question 3 they're asking us to plot the region where z minus 1, the modulus of z minus 1, is less than or equal to the modulus of z minus I. And it's got to also tie in with mod z minus 2i is less than or equal to 1. Okay, so what we're going to look at here is what we've got. So the first one, mod z minus 1, is the length between a moving point z and a fixed point 1. So to draw this nice and big so we can see it, we've got 1 here. That's the point 1. And the point I is here. That represents the 2 points in the first part. And the moving point z has to move so that, firstly, it says that it's less than or equal to. We're going to draw in the or equal to. And the or equal to is a line that goes halfway between these two. And the only way it can do that is so that it's perpendicular to those two. Those two, if you draw in this dashed line here, have a gradient of minus 1, which means this line has a gradient of 1 and is the line y equals to x. Okay, now that's the first one. No, so for it to be less than, the distance from z, which is moving along this line, the diagonal line, to 1, which is the bottom right dot, that has to be less than the distance from the moving point z up to I. So on this line is where it's equal, and below the line is where it's less than. So the region that we shade in to make this true is below all that line everywhere. But we have to consider another place, z, and it's at a second place where it's in the form of a circle. Now the reason we know that is because it's a moving point z with a fixed point that we haven't figured out yet, and it's got to be less than or equal to 1. So the equal to 1 is the fixed point, is the center of the circle. The moving point z is the circumference, and 1 represents the radius. So firstly we need to rearrange z minus, in brackets, 2 plus 2i, so that now it looks like the distance between a moving point z and the fixed point 2, 2i. Now 2, 2i lies on this circle up around here. So that's the point, that's 1 there, that's 1. And 2, 2i is up here. And so the radius, being 1, is there, roughly, there, and there, and there. Now it's not a perfect circle, but it won't be too bad. And because it's less than or equal to, we can draw a solid line circle. Okay, so for that to be true, we need it to be less than or equal to 1, which means we need inside the circle. But it needs for both to be true at the same time. So it needs to be below the diagonal line and inside the circle. So the only region that satisfies that is inside the circle in the bottom half here, because that makes it below the diagonal line and also inside to the circle. So that's how we solve the first part of that problem. Okay, now the second part is a little bit different to what we've done. Because it's arg of something and it equals to a constant, we know that's going to be a line. And we know that the line has an argument of pi on 4, which is just 45 degrees, so it's going to be parallel to the diagonal line. And the arg of z minus 1 is that if you move z, a moving point z, and you find the argument between z and 1, it's 45 degrees. So we start at 1 and draw a line, a diagonal line, from 1, that's going to represent all the times when the argument of z minus 1 equals pi on 4. So there's actually going to be two intersections between this line and the circle. Now, in order to find those 2 points of intersection, you can do simultaneous equations. Once you figure out the equations of the two shapes that you have here, the dotted line that I've drawn in with the argument of z minus 1 equals pi on 4, well, that has a gradient of 1 because it's parallel to the other one, and it is in fact the line y equals x minus 1. Okay, so you can sub in there and find where y equals x minus 1 is equal to that circle, and that circle up here is the circle x minus 2 all squared plus y minus 2 all squared is equal to 1 because the radius is 1. So you can just sub in y equals x minus 1 into this to get a solution for this. So that is the kind of the simultaneous equations method of solving that. Okay, so we're going to sub y is equal to x minus 1 into the circle equation, x minus 2 squared plus y minus 2 all squared equals 1. And when you sub in y equals x minus 1 in that, you get x minus 2 squared, which is x minus 4x plus 4, and then you get x minus 1 minus 2 squared, so that's x minus 3, so you get x squared minus 6x plus 9, and all of that equals to 1. Lost a squared there. Okay, simplifying this all out, you get 2x squared minus 10x. Now you get plus 13, but when we subtract 1 from both sides, you get plus 12 equals to 0. So this is just a quadratic that's non-monic, so we need to PSF that. We'll do that over here. So the product is 24, the sum is minus 10, and the factors are negative 6 and negative 4. So you get 2x squared minus 6x minus 4x plus 12 equals 0. 2x outside of x minus 3. And the other one is minus 2. No, minus 4, sorry. Minus 4 outside of x minus 3 equals 0. Should have divided by 2 first, because you can see there's a factor of 2 that I've left in. So I get 2x minus 4, x minus 3. Now it doesn't matter because the same solutions will come about. It's just less simplified, but you get the solutions being x is equal to 2 and also x is equal to 3 as the two ways to solve that. So what you then just need to do is sub in those values into either equation to get your y value. Easier enough to sub it into the line. So at x equals 2, y equals 2 minus 1, which is 1, and at x equals 3, which is the second solution, y equals 3 minus 1, which is 2. And so, when we're looking for the point P, which satisfies arg z minus 1 equals pi on 4, we get P being the point 2, 1, and the other point is 3, 2, or in the form of complex numbers, P is a complex number with 2 plus I or 3 plus 2I as the two complex numbers which solve that problem.